Welcome, ladies and gentlemen, to a lecture on solving problems using rotational dynamics. Today we're just going to look at another three problems and do them as examples of how to apply these rules of rotational dynamics to solve physical problems. So our first example. Two blocks are hanging on either side of a pulley. The pulley is a uniform density disk with a mass of 0.8 kilograms and a radius of 5.3 centimeters. The mass on the left is 2.3 kilograms and the mass on the right is 1.7 kilograms. Both masses are 1.1 meters above the ground to start. When the masses are released, what is the speed of the 2.3 kilogram mass as it hits the ground? So for this one, if I have some pulley here with a radius r, and I have a mass hanging down and a mass on the other side, and they're both this height h above the ground. I'm going to call this one M2, this one M1, and we're going to call the mass of the pulley MP, okay? And this is a problem we've solved a couple times before, right? We solved it using Newton's laws, and that was kind of a pain, but it was doable, right? Then we solved it with energy, and that was really easy, but we assumed an ideal pulley, okay? Now what we're going to do is we're going to not assume that the pulley is ideal, okay? We're going to assume that the pulley does have mass, okay? And it's going to have rotational kinetic energy when it spins, okay? So the rope going over the pulley, of course, is going to act like rolling without slipping. The whole point of the pulley is that it spins, right? Not that the rope just slides over it. So what we're going to have here is this mass 2 weighs more, and so this thing's going to go this way. The pulley's going to spin this way. Mass 2 is going to go to the ground, and mass 1 is going to go up. So let's list our variables. The radius of the pulley is 5.3 centimeters, right? The mass of the pulley is 800 grams. The mass of block 1 here on the right is 1.7 kilograms. The mass of block 2 is 2.3 kilograms. The height that they start above the ground is 1.1 meters. Okay, and we want to know V final, okay? The velocity of the blocks at the end. Okay, so to solve this problem, we're going to use conservation of mechanical energy. That says that UI plus KI plus work non-conservative is equal to UF plus KF. Okay? So we just start listing these things out. First, the potential energy. Well, at the beginning, we have M2 GH, right? And we have M1 GH. Nothing's moving, so we don't have kinetic energy, and there are no non-conservative forces in this problem. So then on the other side, at the end, if M2 goes down by H, M1 must go up by H, right? So then M1 G has a new height, 2h, okay? So it has this potential energy. M2, of course, is hitting the ground, so it has no more gravitational potential energy, right, in the system that we've set up here. So then I have kinetic energy of each object. Block 1, of course, is moving up with a velocity Vf, and block 2 is moving down with that same velocity Vf, right? Same speed, excuse me. Not the same velocity, right? They're pointed in opposite directions with that same speed Vf, okay? And then, so far, this would be for the ideal pulley, right? But then for the pulley that's not ideal, we have to add in this term for the kinetic energy of the pulley spinning, okay? So again, we have the problem, and it's mostly the same as if we assumed an ideal pulley, right? But then we have this one little term, this perturbation from the main problem. The main problem is this problem with the ideal pulley. And then we add in this little perturbation to account for the pulley actually having a mass and spinning. So then this is 2m1 GH plus 1/2 m1 VF squared plus 1/2 m2 VF squared plus 1/2. And then I, for a solid disk, if we have the pulley be a solid disk, it's 1/2 and then the mass of the pulley times the radius of the pulley squared. And then omega, because the rope going over the pulley is going to work like rolling without slipping, it's this VF, okay, the velocity of the blocks, because that's how fast the rope is moving, over R, okay? That's going to be omega for the pulley. So then we have 2 m1 GH plus 1/2 m1 plus m2 VF squared. That's these two terms above, okay? This one and this one. Plus, now 1/4 mass of the pulley VF squared. So then if I bring my 2m1GH over to the left, what I end up with is GH times m2 minus m1, okay, because I subtracted it from each side. And then on the right over here, I'm going to multiply the whole thing by 4 so we get rid of this 1/4, okay? So on this side, I'll end up with a 4, right? And then on this right side, I'm going to have 2 m1 plus 2 m2 plus the mass of the pulley. And all of that is going to be multiplied by VF squared, okay? And that means that VF equals 4GH times m2 minus m1 over 2m1 plus 2 m2 plus the mass of the pulley. And all of that is in a root, okay? You can see that our units work. We have meters per second squared times meters times kilograms, and then on the bottom it's all just kilograms. That's in a root, so we end up with meters per second, okay? And then for sanity checks, of course, the final velocity goes up as g or h goes up, right? That makes sense. And if it goes down as the mass of the pulley goes up. And that makes sense, because as I bring the mass of the pulley up, I have it taking on more and more rotational kinetic energy, right? So it's kind of using up more of the total energy of the system. So I end up with slower speeds for the masses, okay? And if I plug in numbers, I believe what we find is that VF equals 1.7 meters per second, okay? Now, if I look at my answer, I would encourage you guys to go back and look at when we solved this problem before, and you'll see that again, what my answer comes down to is really a little perturbation that happens because of the mass of the pulley, okay? It's the same answer that I had for this problem when the pulley was ideal, but now I've just tweaked it just a little bit because of the pulley. I've added this mass, okay? And you can see if I took that MP out, I could factor a 2 out of these other two terms over here, and I'd end up with a 2GH on top, and then just these two on the bottom, okay? And that was our answer when we didn't account for the pulley, right? When we had an ideal pulley. So once again, we have a situation where we solved this problem before with an ideal pulley. When we solve it with the pulley accounted for, it's the same exact problem, and we just add a little piece that perturbs our answer from before to now account for the pulley, okay, to make our answer, a little bit closer to the actual physical system that exists in the real world. Okay? Okay, example 2. Suppose you have a mass of 60 kilograms and you are on a merry-go-round that can be approximated as a solid disc with a mass 200 kilograms and a radius of 1.6 meters. To start, you stand on the outer edge of the disc and your friends spin it up to 45 RPM. If you then pull yourself in so you're only 0.2 meters from the axis of rotation, what is the RPM of the merry-go-round? So we have a merry-go-round here. Friends are going to spin it up. Initially, you're going to be out here on the edge, the distance r from the center, and then in the end, you're going to be in here close, what we'll call this distance rf, okay? The mass of the merry-go-round, we're going to call the mass of the merry-go-round big M and us little m, okay? Is 200 kilograms. Little m is 60 kilograms. The radius of the merry-go-round is 1.6 meters. And at the end, we're just going to be 20 centimeters from the inner edge, right? And then omega naught is equal to 45 RPM, okay? And then the question asks, what is omega final? Okay? Now, of course, for this problem, we're going to solve it with conservation of angular momentum, right? Li equals Lf. And how do we know that we can use conservation of angular momentum? Well, we have an object spinning. Okay, that's the first start. If it's going to be angular momentum, obviously we're going to have things spinning, right? And second, there are no external torques on this, right? You're going to pull yourself into the middle, but that's you and the merry-go-round, which are both things that we're considering in this system, okay? So there's no external forces involved there, so there can't be any external torques, okay? So we're free to use conservation of angular momentum here as long as we account for all the things that are in the system. In this case, you and the merry-go-round, okay? Okay, so we have both things spinning in the same direction. The direction's not going to change, but we are going to change the moment of inertia in the system. So we're going to change the magnitude of the angular velocity, right? So L, of course, equals I omega. So for U, initially, we can treat U as like a particle on the edge of this thing. And so your moment of inertia is mr squared times omega naught, okay? And then plus, and it said that the merry-go-round was a solid disk, which has a moment of inertia 1/2 m big M r squared. And then that's times omega initial, okay, which is omega naught. And then at the end, the merry-go-round has this 1/2 mr squared still, but now omega final, right? Plus, and then your moment of inertia at the end is again going to be mr squared, but now it's mrf squared, right? Because you're at this new radius times omega final, okay? And so then what we have is 2m plus big M r squared omega naught equals big M r squared plus 2m rf squared omega final. Okay? And then that means that omega final equals omega naught times r squared over m plus 2m divided by big M r squared plus 2m rf squared. Okay? And then notice that the way the units worked out on this, omega f is just equal to omega naught times some piece, right? Times this fraction over here. So I don't need to do any unit conversions. Omega naught is in RPM, and the answer asked me to find it in RPM. So since all the units in this fraction cancel, right, I have RPM times meters squared times kilograms over meters squared times kilograms equals RPM. Okay? So then I can just plug in numbers, right? I just plug in all my numbers. I have some unitless number in this piece, in this fraction, times the original RPM, and I get the final RPM. Okay? And then if we do plug in numbers, I believe we find that omega final equals 70 RPM if we use the 1 sig fig that this appears to have. Okay? And I think it was 71 RPM if we use 2 sig figs. All right. So the last thing is, I didn't mention the sanity check. I did it when I solved the problem myself, but I didn't mention it here. So the omega final goes up as r squared goes up, all right? And that makes sense because you're bringing yourself in a bigger distance, right? You moved from r squared to rf, so if we keep rf the same and we make r bigger, you're going to move yourself in further, okay? The omega final goes down as big M goes up. So if the merry-go-round has a bigger mass, then your mass is going to be a smaller percentage of the total mass of the system, and that's the mass that you're moving, right? That's the one that you're changing the moment of inertia for. So if that's a smaller and smaller percentage of the system, it makes less and less of a difference, okay? And then by the same token, omega final goes up as little m goes up. And that makes sense because then it's just the opposite, right? You're making your mass a bigger percentage of the total system. That's the one you're changing the moment of inertia for, and so you get a bigger change in the angular velocity. Okay? Okay, and now our last example. Consider striking a billiard ball with the cue stick. Where should the ball be struck so that the billiard ball immediately starts rolling without slipping? So imagine we have a billiard ball here. It's got this center of mass, and then we're going to strike it with the cue like this. Sorry, the idea here is that we strike it horizontally, so we apply the force this way. Some distance h above the center of mass, okay? Because if we strike it right at the center of mass, we won't be putting any torque on the ball, right? So it'll be forced to slide, at least until friction between the ball and the table makes it start rolling, okay? But if we strike it in just the right spot, we can make it not slide at all because we're applying a torque by striking it above the center of mass, okay? So, of course, rolling without slipping means V equals omega R, right? That's going to be important to us. And then we're just going to start kind of thinking about this problem, okay? So if I strike it with the cue, I apply some force. And when we strike a billiard ball with the cue, we generally think of having like a pretty elastic collision that occurs for a really short time, right? If I slow the time down a lot and the cue is touching the ball, of course, I'm going to get some friction between the ball and the cue and stuff, right? But we don't generally have that. We generally have the cue come in and hit the ball, and the ball moves away, and the moment that they're in contact is really short, right? A little tiny fraction of a second. And remember that force times the time that it's applied is the impulse, J. So, let's make this clear. For the linear case, okay? So for the linear case, the impulse, J, is equal to the integral of the time, of the force times the time, okay? And remember that the impulse momentum theorem said that was equal to delta P. And since the momentum at the beginning, the momentum for the ball, right? This is delta P of the ball, right? Momentum would be conserved if we were considering both the ball and the cue when they collide, right? But if we're looking at just the ball, then the change in the ball's momentum is equal to this impulse, okay? And of course, since the ball starts at rest, its momentum is 0 then, and then at the end, it's mv, okay? It's moving with some mass now. And so this tells me that J equals mv, okay? And I've dropped my little vector symbols now because this is all one-dimensional, right? This ball, as far as the linear is concerned, it's all one-dimensional. We're going to make everything move in this direction, right? Okay, so we used impulse to say that the total impulse, because they didn't tell us this time, right? It also didn't tell us this force. But we just know the way that we strike a cue ball, and we've come up with this impulse equals mv, okay? So now for rotation, we're going to have an analog of that, right? For everything else, we had the analog from linear to rotational. For this, we do too. And now we say that the integral of the torque, right, the net torque on the object, dt, is equal to the change in the angular momentum, right? So this is kind of an angular analog to the impulse momentum theorem. Okay. But then remember, the torque is going to be h cross f, right? dt. But then the h and the f are going to be perpendicular, right? H goes like this, and the force goes like this. So they're perpendicular. And so what I end up with is hf dt is the change in angular momentum, okay? But h doesn't depend on time, right? H is just this distance that we strike it above. It has nothing to do with time. And so we can pull it out of the integral, and we'll get an integral that's h f dt equals the change in angular momentum, right? In fact, I took the vector off of f here, so I'll take it off the L as well. And then this integral f dt, that was this right here, right? So then what I find is that hj equals, and then delta L, it has no angular momentum at the beginning, right? And then at the end, it has I omega, okay? So this rotational piece gave us this, hj equals I omega, and this linear piece gave us j equals mv, okay? And all this was impulse momentum theorem applied for the linear properties of the ball, and then the angular analog of the impulse momentum theorem applied for the angular properties of the ball, okay? So we came up with these equations that kind of describe the way the ball is going to react when we strike it with a cue at some distance h here above the center of mass, okay? So now, when we're dealing with the billiard ball, we have a sphere of uniform density, okay, which means that we have a moment of inertia 2/5 m r squared, okay, where r is the radius of the billiard ball, okay? So then, using this equation, we would have h j equals 2/5 m r squared omega, right? But omega for rolling without slipping, which is what we're trying to do, right? This whole problem is, where do we strike this so that it's always rolling without slipping? There's no sliding at all. If that's the case, then omega is going to equal v over r because of our rolling without slipping equation, right? So we'll replace this omega with a v over r, okay? And then that means that we have 2/5 m vr, okay? But then I can take this equation, the linear equation, and I'm just going to use that to divide this equation that I have right here, okay? So on the left side, I'm going to say hj divided by j, the left side of our linear impulse momentum equation, equals, And then the right side, I'm going to divide by the right side of this equation up here. Okay? So I have 2/5 MVR over, and then MV. Okay? Right here. And you can see I get a whole bunch of canceling, and then H equals 2/5 R. And there you go. It's that simple. If I strike this ball with the cue at 2/5 of the radius above the center of mass, okay, so if I divided, let's erase for a second here. If I divided this distance into 5 equal pieces, 1, 2, 3, 4, and then 5 up here, that's equal-ish, then the appropriate place is this point at 2/5 R above the center of mass. That's where the cue should strike, so that this ball never slips at all, okay? It always rolls without slipping. And that concludes our lecture for today. At this point, you should have a pretty nice handle on rotational dynamics, and you should be ready for the next test, okay? Between our lectures, our examples, and the homework, you have lots of materials here to practice using these tools. And if you understand this, the test should be no problem. And at this point, you really have a good understanding of the vast majority of tools that you need to understand most physical systems that you see in the world at least a basic level, okay? So if you make some simplifying approximations for many mechanical systems that you see, okay, you should have the tools now to basically understand how they work and why they work the way they do.